Hey there, CPO here, and I wanted to take a minute to do a quick video on what I'll call Tricopter and T-Copter design theory. And I'm looking at this from the perspective of the design of a symmetrical tricopter or T-Copter. And I'm putting those two together, and I'll show you why here in a second, because they really are the same from a design concept as it pertains to symmetry. So I wanted to start out with the basic RC Explorer style tricopter design. It's 120 degree arms from the center point, and it really is kind of the standard foundation for tricopter design. And just to show you what I have here, I do have David Vindestol's tricopter body here. I've got it partially assembled. I've got the top off, and you can see I've actually got the screw hardware in here so that you can see how this interacts. And basically I just put these rear screws in backwards and use them as pegs to stop the motion here, so you can kind of visualize that. But other than that, it is simply a 3D model that will give us a good reference for some design discussion. So with that said, the standard tricopter design in its symmetry really is a design that is proven historically to be of significance. As a matter of fact, Leonardo da Vinci basically designed the first tricopter. And I'll prove it to you right here. Check it out. This is the Vitruvian man, which is, and no, it's Leonardo didn't invent the tricopter, but if he would have done it with the same symmetry that he did this famous work of art. And the thought behind this is that symmetry, in this case, the human body is a model of symmetry in design. But I found it interesting he uses 120 degrees for his hand placement, which kind of maps out with what we're doing here with the tricopter. So at any rate, that's just some little fun there. But it really is a proven design. And when I say symmetry, I'm talking about the fact that all of these components are equal in various lengths. So motor-to-motor links are going to be the same across all motors, and in this case, the angle is 120 degrees across all three segments of this circle. But I really want to talk about how to take this model and modify it and find symmetry in a different design. So, because that's what I'm working on, is building a modification to this tricopter. I want a little bit wider spread, and I had to think about, what does that mean to the design? Where does my center of gravity go? How do I know how long to make my tail boom if I change the angles of the front two booms? So that's kind of what I'm doing here. The reason I'm calling this Tri and T-Copter is because they really are the same thing. The motor placement is the same on either of them. It's simply just the arm placements that make them different. But if you get rid of, let's say, the booms and the body of the tricopter, and instead of that, let's plug in a T-Copter, you can see it's exactly the same thing. Our center of gravity is going to be in exactly the same place, and basically it's just how we lay out the structure. The flight controller doesn't care if you're using a T or a Tri. All it cares about is where the motors are, where the balance point is, and then and then based on gyroscopes, we'll deal with everything else. So a lot of the things I'm going to talk about will transfer over between the T-Copter and the Tricopter. So let's talk a little bit about the symmetry of the standard 120 degree design. And basically, I was looking at how to find the center of gravity point for this design. And you can think of this in two ways. You can think of it as in triangles or angles, or think of it in terms of circles. I started out thinking of it in terms of circles and find that it maps very well to those of you that like to think in terms of angles or triangles. And there's a lot of great information on the web about, hey, where's the balance point, and a lot of good advice. But I often don't just trust what people tell me. I like to find ways to prove it. It's like, show it to me. So I do my own research and figure out in my own head how things work out. So taking David's original design here, and let's just draw two circles around the front two motors. So starting at the center point here, draw a big circle that touches the center of this motor, and then from this motor, draw a big circle that touches the center of that motor. What that's going to tell you is the optimum placement for your tail motor. So if you have the front two motors sorted out and you need to know how long to make the tail, this would be a good way to do it. Once you get to that point, you can then draw a circle between all three of these points, and you'll find the center of that circle is going to be your center of gravity point. And this actually aligns with what we would expect to be on this particular tricopter body with this setup, where the center of gravity is, where those three booms meet. Now, I have seen a lot of advice about the center of gravity is always where the three booms meet, and that only works if you have 120 degrees between all three booms. But when you start modifying things, it does change it up a bit. So that's kind of where I wanted to do this exercise. Let's take a look at the dimensions. I've got a lot of dimensions here, a lot of things to look at. But for those of you that like angles, you can see here I've got a triangle. The old adage of draw a line between your front motor and rear motor, and then a perpendicular line from that will point to the center of gravity. That proves to be true in this situation. Keeping in mind this is a symmetrical tricopter, meaning that it fits within a circle, a pattern of a circular pattern. So I'm ignoring the fact that it's possible to have shorter booms or longer booms and still have great flying tricopter. I'm basically trying to start out with the most simple and basic design for a perfectly balanced copter, regardless of what the flight controller is going to do with it. So this should be a naturally balanced flying machine, even without a flight controller to manage the attitude and all that. So going back to the measurements, I have a boom to boom, motor to motor of about 582. You can see I'm close here. I'm doing manual measurements here. So 582, 582-ish, 582-ish. I've got a total disc circle diameter of 672 millimeters. And then you can also see some things here like how far from the motor to the center of gravity point. I have it 336, and how far from the line that goes between these front two motors down to the center of gravity point. Now again, keeping in mind, Tricopter and T-Copter look the same when you get rid of the just the body and the arms. So if you look at the T-Copter, this should look very familiar to T-Copter builders as far as how to lay out T-Copter. As a matter of fact, there's a great T-Copter calculator on the internet, lloydhassel.brinkster.net, RC Groups T-Copter Dimensions Calculator. You can search for it. It's on RC Groups. That's where I found it. But he kind of put together this calculator to help make this easy, which looks at the motor-to-motor links of the three. Again, this is a symmetrical design as well, and then we'll help you calculate how far from like your rear motor to the center of gravity point your T-Copter will be. So let's plug in the numbers I have. We'll say 582 as my average motor-to-motor values here. So if I plug in 582, what do we get? 336. Let's go back to the design, 336. So basically, I come to the same conclusions that he does with this calculation, using these figures of 86.6% of A and 33.3% of B, and D equals A divided by, that's great math. That didn't make sense to me. What made sense to me was drawing some circles, seeing where they intersect, and then figuring out my my center of gravity from that point. So going back to what I started with, all I really needed to know was draw the two big circles, figure out where my tail needs to be. Once I know where my tail is, draw the big circle that connects them all. Right in the middle of that is my center of gravity point. And again, that doesn't matter if it's a tricopter or a T-copter. Going back to the tricopter design, same thing, center of gravity is right there. So with that said, what happens if we modify these dimensions? So as an example, David, in his flight test scratch build tricopter video that he did, he actually builds one of these, and this is the standard 10 millimeter booms that he used with his original design. When he built the flight test scratch built tricopter for us, he actually used 12.7 millimeter booms, or half-inch booms, which are readily available in all the hardware stores around here. But it changed his design a little bit. So actually, if I go in here and let me take this from a 10 millimeter boom to a 12.7 millimeter boom. And I need to make a couple other changements for center points for my holes so that they stay centered. All right, so now I just put 12.7 millimeter booms on this. Okay, everything is the same. I've still got 120 degrees, got all this, but there is one problem. With the larger booms, I'm actually violating the rules of matter, which says two objects of matter can't occupy the same space. So what I need to do is adjust these arms so that in real life, they would actually hit the edge of that, which is the stopper screw or bolt or whatever you want to call it. So that's going to be the new angle just by switching from 10 millimeter booms to 12.7 millimeter booms. Our new angle is 128 degrees. And that's all we did, was change the width overall of our booms. So that changes some things. So as you can see, our circle is no longer lined up with our motors. Our motors are further apart now. Our center of gravity is likely to be different from that, but we don't know exactly how much different until we do a little bit of work. So let me get rid of the two circles here for the 120 millimeter setup that I used. And let's take a look at the circles for the 128 millimeters. So I did the same thing I did before. I started with one motor, drew a big circle, started with another motor, drew a big circle, and then now I see where they meet. But guess what? We're not there yet. So what we need to do is extend this rear boom so that our motor comes down to this point. Now David does this in his video, maybe not to the same degree, but he does have to extend the rear boom, and he talks about that a little bit. So maybe this is why. So basically I'm just going to take this rear boom, drag it right down to its position. So that would be the optimum length of that rear boom. You'd have to sort out, obviously, we'd have to actually lengthen the boom. We can't just drag it out in real life. But for the purposes of this, that gets us where we want to be. Now that I've got that, I can draw my disc circle between all three of the motors and then identify my new center of gravity point, which is right here now, is the middle of the circle. As a matter of fact, let me plug that in. So the old center of gravity was up here. We used 12.7 millimeter booms instead of 10 millimeter booms, and the center of gravity goes from here to here. fairly significant change. Your flight controller probably won't care, but for natural balance of the tricopter, it's better to now balance it from this point, which means your flight controller typically should go over the balance point if you're building it as precise as you can, which means we're going to have to try and find a way to get the flight controller down here. But everything else looks the same. Everything else works the same. You still have the straight line between the motor, the front motor, and the rear motor with a perpendicular line that points to the center of gravity. We do have longer motor-to-motor links, 604 it looks like here, ish, 603. You've got a larger disc size, so it was, what was it before? It was 672, now it's 697. So a little bit larger disc area because we've expanded that circle. But your formula will still work. As a matter of fact, let's plug in 603.50 into the calculator now. And it's 348 and a half-ish, somewhere around there. And 348 and a half is what I come out with here. So you can see that calculator really is effective. And again, tricopter, T-copter, doesn't matter. If you just look at the motor positions, the substructure shouldn't matter. So that's basically what I wanted to go through, was just a quick look at some ways to figure out optimum center of gravity and optimum boom placement and positioning for your tricopter. As you're aware, I'm doing a build, and I plan on potentially, I'm still leaning towards 135 degree spread on the front booms to give me plenty of room to avoid GoPro camera stuff. So if we look at what that might look like, you can see here I've got to actually bring the motor down to that point. Oops. Let me unhide this. It'll make it a lot easier on me. So if I bring my motors down to the 135 degree mark, you can see how much longer my rear boom has to be in order to fit the symmetrical design of the standard tricopter. And my my disc gets a lot bigger, 715 millimeters, so quite a bit larger. But all the math still works. My center of gravity point changes and goes to a point where it's almost unusable on this particular frame, which is why I'm working on developing my own version of a frame. But I could use this center of gravity point just like the T-copters do, strap the battery back here somewhere, flight controller mounted up here or whatever. I've actually been looking at building my own body. Right now my design looks something like this, and I'm still playing a little bit. Let me hide this RC Explorer one. I'm still looking at a little bit of options here as far as how do I want this to work. But I've got a spot built for the flight controller right here, right on top of the center of gravity point. I may do some changes. I may change the pivot points. I don't really want to pivot into, so I might use this as the pivot point and pivot on the outside. So I'm still working that out. That'll be a work in progress over the next couple of weeks. But at any rate, my plan is to, again, take a 135 degree spread and then adjust my body to match accordingly. So that's about it. I just wanted to go over that with you real quick. Sorry it was a little bit long, but I wanted to take some time because I did a lot of research and looking around with regard to tricopter design, and there's just not a lot of information out there. So I thought it would be nice to share what I have learned And then again, also go into a little bit of, I'll call it theory. It's loosely theory. I find it somewhat interesting, but you know, there is some logic to how these things are laid out. And starting with David's design was a perfect place to start because it's a proven solid flyer. So hope that's it. If you have any questions, let me know. If you have any feedback, always appreciated. And if I'm missing something, let me know. I mean, again, I'm making some assumptions here that we're looking at a symmetrical tricopter design. I realize there's things like yaw authority or you know, inherent instabilities with certain types of designs. Right now, I want to start with a foundation of a symmetrical, circular-based tricopter design, and from there, I will play around with more of some of the other more advanced features. I've never even flown one of these before, so I want to build one that's a nice, stable, steady flyer, and then I'll start playing with other parts of the experiment. But anyway, hope you enjoyed this, and you know, give me a thumbs up if you liked it, and again, give me some feedback if you have some. So I appreciate it, and thanks for watching. I'll catch you on the next one.